is we're going to be looking at the rational root theorem. Yesterday we did what was the theorem we looked at yesterday? Remainder theorem. That's right, I forgot for a second. The rational root theorem. Okay? The theorem is going to have some given information. Right? Our given information for the rational root theorem is polynomial function p of x, it's a function of x, equals, y'all pay attention now, c sub n x to the n. It's an nth degree polynomial. The next term we're going to call c n minus 1 x to the n minus 1. So, in other words, my powers of x are stepping down by 1 each time. And c sub n stands for the constant that goes with the nth degree term. C sub n minus 1 is the constant that goes with the n minus 1 degree term. And that's going to continue with a bunch of stuff in between to c1x to the first power plus c naught, c sub 0. Okay, and that c sub 0 is our constant term. Right? So c sub n is the leading coefficient. C sub 0 is the constant at the end. Now, just like we've just seen with all of these examples that we've worked, the denominators were all factors of what? And here, the 2 and the 3 were factors of 6, right? The 2 and the 3 here were factors of 6. So the denominator of our rational numbers are going to come from the leading coefficient. The numerators of our rational answers are going to come from the constant term, factors of the constant term. Okay? So, if P over Q, or this is a rational number, is a solution or root, let's call it a root since this is a rational root theorem, root, 0, x-intercept, solution, synonymous terms. If we have a rational solution or root, then P is a factor of, the numerator is a factor of the constant term, and the denominator is a factor of the leading coefficient. Now this is not, if anybody watches this on YouTube, they got a PhD in math. Well, you forgot about this little thing. I'm giving you guys a college algebra rendition of this rational root theorem. It's pretty solid as it is. Okay, but the numerator of our rational solutions will be a factor of the constant term, and the denominator of our rational solutions will be a factor of the leading coefficient. Okay, so that's what the rational root theorem gives us. Now, the problem is a lot of polynomials don't have any rational solutions. Okay, that's why this condition at the very beginning says if P over Q is a rational root. So just because we can come up with some rational common numbers that are combinations of the factors of these two things doesn't mean they're going to be solutions. We're going to use the remainder theorem from yesterday to guess and check, see which of those rational solutions work in the polynomial and which ones don't. If we can find one, then we'll take the quotient that we got using the remainder theorem, and we'll find the remaining zeros of that function. Okay. Some of the problems on your next test related to this is I'm just going to say state all the possible rational zeros. I just want you to understand that the possible rational zeros come from the factors of the constant term at the end divided by the factors of the leading coefficient. So that's how it'll work. So this one that we did on the board right here would have a lot because 6 and 15 have a whole lot of factors. The possible numerators, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. That's the possible numerators. Possible denominators are factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. There's a lot of fractions that you could put together from those combinations, right? So 1 over 1, positive 1 or negative 1, positive 1/2 or negative 1/2, positive 1/3, negative 1/3, positive 1/6 or negative 1/6. Positive 3 over 1 or negative 3 over 1. Positive 3 over 2, negative 3 over 2. You see how it works? 3 over 3 gives you 1 again. 3 over 6 gives you 1/2 again. But those are the possible rational zeros of that polynomial. Of course, if we have a quadratic, we're not really interested in that because we're just going to solve it using one of our quadratic techniques and move on. But if we have a 3rd degree, 4th degree, 5th degree polynomial, we want to find some rational zeros so we can reduce it to a 4th degree, find some more rational zeros so we can reduce it to a 3rd degree, till we can reduce it to a quadratic that we can solve with a quadratic technique. Okay? So let's look at an example. Find the zeros of the given polynomial function. Go ahead and write this down. The first thing we're going to do is list the possible rational zeros. If we can't find a couple of rational zeros to reduce it, then we're just not going to really have the techniques to solve it algebraically. We'd have to use a graphing technique to solve it. Okay? But these are kind of problems that are set up nice for you that you can solve. So what are the possible rational zeros? We're going to abbreviate that. Possible rational zero, PRZ. What are they? The factors of this number divided by the factors of that number. But this is just 1, so that's a gift. So we're just looking at the factors of 12 over 1. What are the factors of 12?
3.
Plus or minus 1, 2. These are all numbers that divide 12. Those are the possible rational zeros. Okay? So we want to guess and check. We're going to let this PowerPoint guide us because it already knows what the zeros are. Let's try probably where would you start first if you were just trying? Let's go with the gut. Where do you want to try? Miller, which number you want to try? Pick one. 4. Attaboy. 4. So put the 4 there, and we're going to evaluate it using the remainder theorem from yesterday and see if it gives us a, what are we wanting right here? If it's a 0, we want 0, right? Bring down the 1, that's 4, 7. It's not looking promising, is it? 28. Multiply by 28, it's not going to give us anything that works very well. Okay? So 4 doesn't work. 6, you want to try 6? She meant 2. All right, let's try 2. Well, let's try negative 2. We're going to go with this one. All right? That was my baby girl, by the way. Let's try negative 2. Bring down the 1, right? Negative 2 times 1 is negative 2. 3 minus 2 is 1. Multiply that, you get negative 2. Negative 4 minus 2 is negative 6. Multiply that, you get a positive 12. And negative 12 plus 12 is 0. So we found a solution, right? Now, why is it important to use this process to see if it's a 0? Couldn't you just plug it into the polynomial to see if it's a 0? Couldn't you just plug negative 2 in for x in all of these situations right here? We could plug negative 2 in there, plug negative 2 in there, plug negative 2 in there, and it would tell us that negative 2 is a 0. Why is using this process valuable to us? Do what?
Quicker.
It is quicker. Why else is it valuable to us? because it tells us also that x plus 2 is a factor, right? If negative 2 is a 0, then x minus negative 2, we saw that yesterday in the remainder theorem, is a factor of the polynomial. All right? This polynomial will factor as x minus negative 2 times what? X squared plus x minus 6. That's why this process is important, because it actually gives us the factorization. It tells us that the remaining zeros of this polynomial, here's one of the zeros, the rest of the zeros come from the output value here, x squared plus x minus 6 equals 0, which we can solve by a quadratic technique, right? Quickly we can factor it. X plus 3 times x minus 2 equals 0. So the remaining two zeros are negative 3 and positive 2. Now what have we done here? We found all three zeros of our third degree polynomial. That's the end game, right? Fundamental theorem of algebra, find the end solutions to an nth degree polynomial equation. Now, if you've had pre-cal, you've seen this before. Maybe you've seen it in an honors algebra 2 class, but not likely. So this is something that's beyond what you would have seen in algebra 2. All right, any questions here? Now, it's worth mentioning, it doesn't really fit well with what we're learning today, but it's worth mentioning that this is factorable. It's a 4-term polynomial. You can factor it by grouping. X squared times x plus 3 minus 4 times x plus 3. That's x plus 3 times x squared minus 4. Here our solutions are negative 3 plus or minus 2. Okay? So that's another technique we could have used for this one. Something you should look for if you're just tasked with solving an equation. All right, let's look at one more example. All right. X cubed minus 13x plus 12. Always when we're using this, we're trying to find rational zeros so we can reduce the polynomial, and we got a possible rational zeros are going to be what here? The factors of this divided by the factors of this. I love it when the leading coefficient's 1. We don't have any fractions to worry with. We'll look at some tomorrow that involve fractions. So the possible rational zeros, Bryce, are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 4, I missed 4, plus or minus 12. Now, some of the test questions, or a test question or two on the next test will just be state the possible rational zeros. Okay? All right, what do you want to try? You see anything that might, let's just start with 1 and roll into it. Let's do 1. 1, negative 13, positive 12, right? Right? Wrong. What am I missing?
X squared.
0x squared. If you forget that, you're just not going to be in great shape. Okay? Does it work? It does work. So 1 is a root of that equation, a 0, an x-intercept, right? The remaining polynomial that we have to work with is 1x squared plus x minus 12, and I want to solve that equation, see where that's equal to 0. And I'll do that using a quadratic technique. In this case, factoring, right? So this will be x plus 4 times x minus 3 equals 0. So my other two solutions are 3 and negative 4. I found all three roots, three zeros of this polynomial function. It's really pretty slick, isn't it? Okay, let's look at one more together, and then I'll give you one to work on for homework. And then tomorrow we'll practice this some more in class. And this just shows you that if you tried 2 first, and that's not a number that we suggested, it's not going to give you a 0. If you don't get a 0, then you have to try something else. And I think they tried some other number here. They tried 3, just randomly chose a 3 there. And that gives you a 0. And if you'll notice, their trinomial that was left over was different from ours because they found a different 0 first. But it still factors x squared plus 3x minus 4 factors and gives you the other two zeros. It's the same zeros, just a different path to the same answer. Okay? Let's look at this one real quickly. What are the possible rational zeros? Plus or minus 1, plus or minus 5. I like it. Not very many to try. Let's try 1 first. It's the easiest one to try. Why not? Unless you can see right out of the blocks that it won't work, try 1. That gives us 1 times 1, which is 1. That's 6. 1 times 6 is 6. That gives us a 5. 1 times 5 is 5. That gives us a 0. And the remaining polynomial, the quotient of x minus 1 and x cubed plus 5x squared minus x minus 5 is x squared plus 6x plus 5, which will factor as x plus 1, x plus 5. So my other two zeros are going to be negative 1 and negative 5. Okay, now it's worth noting, again here, y'all watch. It's worth noting, and this is on the table when you have to solve one of these, that this polynomial that we started with is factorable. X squared times x plus 5 minus 1 times x plus 5. X plus 5 times x squared minus 1. 3 solutions, negative 5 plus or minus 1. It's a little quicker if you see that it's factorable. It's worth trying, right? If you have a 4-term polynomial, try factoring it by grouping. All right, your homework problem that I'd like you to do is this one. One problem. Yeah. And then tomorrow we will practice this some more in class. We won't move forward. And the ones we look at in class tomorrow are going to be a little bit more challenging. Y'all have a great day.